All right, I finished my general announcements and gave students time on page 12 to complete the multiplication. The highlights of my announcements, most recently we took CFU number 4. Students have today and tomorrow to make that up. Students will receive it back next week on Monday, and you'll have a week to retake it. Students also received grade reports. And one thing I wanted to make clear is that when interims hit, anything that's past dead, anything that's a 0, no longer can be submitted. So if you have any zeros in your grade report other than the most recent grades, like CFU number 4 and homeworks 8 and 9, which were just collected 2 days ago, if you have any zeros that are more distant than that, today and tomorrow are your last chances to replace those zeros with some kind of credit. Okay, because interims close everything that we've done so far this marking period. All right. So we're going to move down to the bottom of page 12. As I said earlier, we're going to start with a problem that hopefully is pretty straightforward. As create an accurate graph for each function by plotting at least 5 points on the graph. Identify each characteristic of the graph, right? D and E for any that do not exist. So my hope is that we've gotten to a point where we are very comfortable typing this type of equation into our calculator. Okay, we go to our calculator, we go to y equals, we type x minus 1 squared minus 2. And our goal is to create this graph. Now you can hit graph to see the thing you're trying to create, but ultimately you go to the table to get the values. And remember, you do not take any numbers that are bigger than 10. So the furthest down I can go is 4, because once I go to 5, there's a 14. And the furthest up I can go into the negatives is -2, because once I get to -3, I also see a number bigger than 10. So I said before, I don't care which points you take, but look for whole numbers, avoid the decimals, it's easier to graph, and look for numbers smaller than 10. Okay? So if we graph this correctly, this is the image we end up with. I'm going to pause to give you a chance to copy here. All right, thank you very much. Point of symmetry is at 1, -2. The point of that is that if you were to cut this thing perfectly in half to create 2 halves, you'd be cutting it through that location. This is where you'd want to cut the graph in half. Okay, now this graph has no endpoint. Think of it like a road. Okay, I understand the road turns, but that's not the same as a road ending. This graph goes forever on the left side, it goes forever on the right side. It doesn't stop, so there's no endpoint. Okay. How about the domain? Can anyone help me out with the domain? How far left and right does this thing go? Yes? Perfect. Positive and negative infinity. You got it. Okay, this thing goes to the left forever. It goes to the right forever. Now, it doesn't do the same thing with range. You got the range too? Go ahead. -2 and perfect. I just wanted to make sure you didn't say negative infinity. Okay, -2 and positive infinity. Okay, the lowest down it goes is -2, but it goes up forever. Okay. Now, in terms of your increasing, decreasing interval, remember you want to read this thing from left to right. It has both. It has a part that's going down and it has a part that's going up. And I understand this can be confusing for people because when you look at the picture, you might interpret it as 2 parts that are just going up. So you think, isn't the whole thing increasing? But this is why I keep stressing you have to read the graph from left to right. If you imagine getting on this graph way over here on the left, way over here up in the clouds somewhere on the left, the moment you hop on that roller coaster, I don't care how far to the left you go, once you get on it, you are coming down, 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 and you don't stop coming down until you get to that point at the very bottom and an x value of 1. So this thing is always going down until you get to 1. Okay. That's why the decreasing interval is -infinity to 1. That tells me, okay, I've got this thing that's always going down, always going down, always going down. But when I get to an x value of 1, I stop. And then starting in an x value of 1, you're going up, which is why this thing is neither. Okay. The only way we call it an an increasing function is if it's only going up. And the only way we call it decreasing is if it's only going down. So for example, if this part of the graph wasn't here and it looked like this, then fine, I'd call it an increasing function because it starts at the point 1, -1, and then just goes up. But if we instead pretended like this part of the function isn't there, Well, then it's a decreasing function because it's always going down until it stops at that endpoint of 1, -2. Okay? Questions? All right, so I want to stress one more time. A lot of you did really well in the CFU yesterday, but that doesn't mean you, and that's what this material is. This basically is what CFU number 4 yesterday was like. Okay? And this is the type of problem we practice in class right before the CFU. But that doesn't mean you can just let that knowledge just fly away from your brain. We're going to take a test at the end of this note packet, and we're going to take that test on Tuesday, October 8th. And it's going to cover everything in this note packet, which means you have to remember how to do this stuff a week and a half from now. Okay, so start thinking about how are you going to organize your notes? How are you going to organize your papers so that you can still recall this information? A really great way, by the way, is keep track of CFU number 4. Don't lose that paper. Go back to it when it comes time to review and study. All right, so remember again the point of the next 2 pages, which I'm going to basically walk you through. On the first page, we're going to create a graph that is a function. But then when we create the inverse, we're going to end up with something that's not a function. And we're going to kind of talk about what's going on and why that happens. But then with the next page, we're going to try to address that issue. We're going to try to graph the exact same function, but we're going to do something with it. We're going to do what's called restrict the domain. That way, when we invert it, we end up with something that is still a function. Like that's the point of today's class. How do you take something that normally, when you invert it, you don't get a function? How do you alter it so that when you invert it, you do still get a function? That's the goal. Okay? Now, the nice thing is it's going to start with some stuff we should already be comfortable with. Part number 2 says f of x equals x squared. Use this to respond to all parts of this question, which is this page and the next page. So we're going to be stuck with y equals x squared for literally the rest of the class. Let me go to y equals x squared. That's the graph we're going to be using for the rest of the class. Pretty straightforward function. Okay. Part A says graph f of x on the coordinate grid using at least 5 points. Record these points in the table. So again, if I go to my table, okay, don't take points that are bigger than 10. So don't use the -416 point. But you can use -39, -24, -11, 0, 0, and you can go all the way down until you get to +39. I don't care which points you want to take. Just take the whole number of points that are smaller than 10. And you end up with the following graph. That's part A. Graph y equals, or f of x equals x squared. So that's part A. Part B says convert the points in your table for f of x to create points in the table for f inverse. So remind me, what do I do to my table of my function to turn it into the inverse table? What do? You switch the 2 sides. You got it. So you take the x's, the -3, -2, -1, and you flip it to the other side of the table. And then you take the 9, 4, 1, 0, 1, and you flip it to the other side of the table. That's part B. Now, part C says graph it. Graph f inverse on the same coordinate grid using the points that you recorded in the table. So I'm going to temporarily change this to orange. That way, when I show you the graph, you can kind of distinguish between the original function and the inverse. Okay? So I'm going to switch it back to blue in a moment, but I just want to make it clear so that people can see the different shape. The original function was a U that faces up. The inverse function is a U that shoots to the right. And by the way, remember, all that happened here was the original function was reflected across this line, y equals x. That's all that happened. We took the blue U that's face up and reflected it across that diagonal line. That gave us the orange U facing to the right. Okay, but let me bring the colors back in correctly here. Okay, so this is what your paper should hopefully look like. Of course, I have a couple points in green because you don't have to do all 7. But I like to do all 7 just because it helps me draw the curve more accurately. All right. All right. Part D says identify the following characteristics using interval notation. So we want to find the domain and range of the original function, the domain and range of the inverse function. Let's start with the original function. So let me fade this one out for just a moment because that's not the one I want to talk about. I want to talk about this one first. What is the domain of this function? How far left and right does it go? Infinity on both sides. Negative infinity all the way to the left, positive infinity all the way to the right. So that is the domain of the original function, negative to positive infinity. How about our range? How far up and down does this thing go? I heard infinite. It goes infinity up. It doesn't go infinity down, though. What's the lowest it goes going down? 0, exactly. It bottoms out right at the bottom of the x-axis, right where the y value is equal to 0. So your range is it goes as low as 0, but then it shoots up forever. Now, we could have a similar discussion using the inverse. I could go through the same questions with you all, like how far left, how far right, how far up, how far down. But I would argue there's a much faster way. What do I do with the domain and range of the original function to create the domain and range of the inverse function? Say again. Reflect is close, but yes, I basically want to switch them. Here's the idea. Domain comes from all of the x values. Range comes from all of the y values. Well, when you're going from the function to the inverse, all you're doing is switching the x's and the y's. So these x's right here for the original function become these y's for the inverse function. Does that make sense? And these y's for the original function become the x's of the inverse function. So they do flip positions, basically. And if you don't believe me, I can go back to the picture. I can prove it to you. I'm claiming that the inverse function in a left to right direction goes as far to the left as 0, but then goes to the right forever. And if you look at the inverse function, that's exactly what it does. It goes as far to the left as 0, but then shoots right forever. So this domain makes sense. That is the correct domain. And by the way, it goes up forever, it goes down forever. So this range also makes sense. Okay. All right. Now this asks, is the inverse a function? Why or why not? Now, again, I'm going to want some help from you all. This is asking us to look at the inverse. Okay. Let me back up and talk about the original function first. Okay. If I asked you, is this a function? Now, this is actually a topic, believe it or not, we talked about in the very first week of school. It's a specific test you can run. If I gave you this picture and I said, why is this a function? Does anyone have any idea what test I'm referring to that you can use to know that a graph is, in fact, a function? Yep. Can't hear you. So it is actually, the inverse is not. You're right. If you're talking about your answer down here to E, you're absolutely right. It's not a function. But I want to talk about the original for just a moment. Okay. Why is this a function? What's the name of that test that we can use? Yep. The vertical line test. Now, let me remind you all, let me show you a picture of this real quick. If we take a vertical line, it doesn't matter where you place this vertical line. Okay, no matter where you put this vertical line, it's going to hit this function only one time. It hits it once, it hits it once, it hits it once. It doesn't matter where I position this vertical line, it only hits the function one time. That is what we call passing the vertical line test. So the original thing is a function. But the question you're being asked about down here is the inverse a function? And when you take this thing and you create the inverse, clearly a vertical line would hit it more than once. Does that make sense? And this is what we call failing the vertical line test. Remember, this is the thing that I told you all we were going to try to fix on the next page, the last page of the day. So no, it fails the vertical line test. All right, now the question at the bottom is sort of the whole point of the next page. So let me be clear, this is not a question I'd expect you all to be able to answer right now. I haven't really taught it to you yet, but this is sort of the whole point of the entire next page. It says, if we restrict the domain of f of x equals x squared to 0 to infinity, will its inverse be a function? Explain. Now, the simple answer is yes, it's going to be a function, but let me show you visually what the heck this question is saying. It's basically saying, what if you only took the positive values of x for this function? What if, when you go to your table, you don't take -1 or -2 or -3 or -4. You don't take any of those. What if you start at 0 and you only take the points after that? 0, 1, 2, 3, 4, 5, 6, so on. Now, visually, what this is going to do is for the original function, you're going to basically only take the right side of the graph. You're going to pretend this side of the graph doesn't even exist. That's essentially what the question is getting at. Does that make sense? And it's asking if you do that and then you invert it, which is going to cause it to look like this, except now, because we ignored that part of the graph, this part of the graph isn't here anymore. It's saying, well, now is the inverse a function? And yes, it is, because a vertical line would hit the inverse. It would hit this part of the graph exactly one time. So suddenly, by ignoring 1/2 of the original function, the inverse gets turned into a function. Okay? So that's what I'm going to pick apart a little more slowly on the next page. But the answer here is yes, it would pass the vertical line test. All right, last thing of the day. On the coordinate grid below, graph f of x equals x squared with a restricted domain of 0 to infinity. So again, what this means is don't take any of the negative values. Start at 0 and take only the positive values. That's going to get you this. That's part A. Now, part H says calculate the inverse. Hint, the first step is to convert f of x to y. So this is actually an old skill that was covered on your previous test. In fact, there was a problem like this on the test that you all just got back today. Although it wasn't this simple. It was a bit more complicated on the test. So step 1 is you change f of x to y. Anyone remember what you do with the x and y next to solve for an inverse? You switch them, exactly. I mean, hopefully people are noticing a theme. We keep talking about inverses. We keep talking about switching x and y. Okay? So this is x equals y squared. You then solve for y. So can anyone tell me what is the opposite of squaring a number? How do we get rid of that squared? Square root. Okay? So we take the square root of both sides. Thank you, Ibuka. And that gets me square root of x is equal to y. And then the final step is change y back to inverse. Okay, so the original function is x squared. We graphed a part of it. We've calculated the inverse as the square root of x, and that's what we're going to graph next. Part I says graph the inverse. Now, if you wanted to, you could go to your calculator and type in the square root of x, okay, and you could graph it, and you could go to the table and copy the numbers. You can do all that. You know, you can get 0, 0, and 1, 1, and 4, 2, and all that good stuff. But what I would say is you already have some points. Just take those exact same points and flip them. Okay, and then when you graph those, you get this. You get something that is a function. Suddenly, this restricted x squared thing has an inverse that is a function. They have a ton of things in common. Can anyone tell me, look at the orange one that I highlighted. What is the domain of the orange graph that I've highlighted? How far left and right does it go? 0 to infinity. You look at the orange curve, it starts at 0 and goes to the right forever. And notice the green one does the same exact thing. It's actually kind of a coincidence that that happens. It doesn't always happen that way. What about the range of the orange function? How far up and down does it go? Same exact thing. It starts at 0 and goes up forever. This is actually why the green had the same thing. For orange, it starts at 0, goes right forever. It starts at 0, goes up forever. So its domain and range are the exact same thing, which means when you switch them to create the domain and range of the inverse, well, you're switching two things that are the same, so you just end up with another thing that's exactly the same. Now, here's the other thing. Originally, x squared is not, that's the red one. Originally, it's not an increasing or decreasing function because it has both. But what kind of functions are these now? Are these increasing or decreasing functions? Increasing. They're always going up. You got it. Thank you for helping me move through this material so quickly. I appreciate it. Anyone who's not keeping up with Ibuka here, because he's giving me a lot of answers today, you've got to speak up if you're confused. Okay? But he's absolutely right. Both of these are increasing functions because they only increase. They don't have any part of them that goes down. They only increase. All right, we moved through that page pretty quickly there. If that's too small for anyone to see, let me know and I'll zoom back in. But I just wanted to get the full page on recording. All right, so we've got a little less than 10 minutes. Not too bad. I'm going to donate that time to you all to work on your homework. Remember, that's homework number 12 at this point. So earlier in the week, homeworks 10 and 11 were assigned. Next week on Tuesday, you're turning in homeworks 10, 11, and 12. Okay? With that being said, I'm done. Thanks for watching. Have a good one.